Okay, now we're back again. So we're going to, as I say, construct this image or something like it from the theory that we've done before. So we need to generate some image points. So to do that, I'm going to generate what's called a function here, which is a line joining any pair of the vertices in this figure. So so J and K are what are called formal parameters, and you can see that it has the form of a vertex J plus some parameter lambda times a vertex K relative to the vertex J. And I'm now going to generate a total of 606 points on the 6 lines forming the wireframe here of the tetrahedron. And I do that using this command. I make a table of this line 1, 2, and I do it for 101 values of lambda, starting at lambda equals 0 and going up to lambda equals 1 in steps of 0.01. And we'll suppress this output because we don't want to see it. So we've got those coordinates, or we've got the coordinates of the points on the image. So we now need to establish the camera parameters. So we do that by first of all establishing the focal length, which in our units will take to be 3. And now we want to assign numerical values to the viewpoint, so we're going to put the viewpoint at the point 5, minus 7 and 5. So that's it. And now we want to calculate the camera axis vector. Well, to do that, we need to point the camera at the object. So what I'm going to do here is to compute the position of the center of mass of all those image points. So I take each image point from 1 up to the length of that table and subtract the viewpoint from it, and then divide that by the number of points, and then assign values for the viewpoint. So we do that. So the camera will be pointing roughly at the center of the tetrahedron. And now we want to normalize that. So we do that, and that's the direction of the camera axis vector. And now we take our formula or expression for that in terms of the polar and azimuthal angles, and we calculate the value of phi using the azimuthal angle as the arctangent of the first 2 elements of this. This is the arctangent with taking regard to the signs of the 2 components here. And we can get an equation for the polar angle by taking the normal, this vector, and subtracting from it the expression for the 3rd component of our camera axis vector, and that gives us that. And I can solve that for sine theta by using this, by setting this equal to 0, and this will tell me what the solution of that is. And now I want to, since the principal domain of the arcsine function is minus pi over 2 to plus pi over 2, then I can calculate the angle theta from that. and then I can apply that to the screen normal, or assign those values into the screen normal thing, and seen to be equal to the center of mass vector, or the axis vector computed above. So that's the camera axis vector taken care of, and now I want to calculate a table of the screen coordinates of all the image points. So I make a table here over an index n, which is the number which runs from 1 to the number of points, which is 606, and I take out my expression for the screen coordinate vector, and then I replace x, y, and z by the values in those contained in the table of points on the object. Again, that's a very long table, so we don't want to see it. So now I've got all those points, and I want to visualize them. So what I'm going to do is to plot all of them using the two-dimensional Mathematica function list plot, and doing that. And there's a picture of the tetrahedron viewed from the point I mentioned. So that's the end of the story, and I hope illustrates that using these various software and hardware things that you can interest material. So let's shut the file down.